Hello, thanks for joining us. This is Space Nuts, the astronomy podcast with Andrew Dunkley, your host, and we talk astronomy and space science. Coming up on today's episode, we are going to be visiting Europa because some exciting things have just been done involving the Juno space probe, and now we've got some data to play with. There's also a story about some great photos that have been taken and processed that are absolutely unbelievable of Europa. Then we're going to talk dark matter. So there's been some new gravitational lenses discovered and they've been able to give us a bit more insight. And we'll answer some questions. Ian wants to know about Venus and Mars, that great Paul McCartney album. Possibly not. And perception of the size of Earth as we look at it, which seems a bit strange to Ian. Yeah, I think the Earth is strange too. And Gus wants to talk about dark matter because he keeps running into walls. So that's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us, as always, is the good Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
I'm well, thanks. How are you?
Very good. Yeah, very well. I just heard a pitiful meow from.
I was going to ask you about your cat. What's the cat's name again?
Muscat. Yeah,
okay.
He's sitting outside the window. This is a wall-to-ceiling window. That's in front of me, and he's sitting outside there, meowing to be let in, even though he knows full well that this window doesn't actually open. It's not the one he ever gets in at.
Does he sound something like this?
No, he's far more pitiful than that. That's quite assertive compared with Muscat.
Yeah, I'm playing with my sound effects again.
Yes. Well, he's probably providing my sound effects anyway. I'll let him in later, but I won't let him in through this window because it doesn't work.
Fair enough. Yeah. Now, we've got a lot to talk about, so let's get stuck straight into it and focus on the ice world of Europa because, Juno has been sort of orbiting the host planet that Europa orbits, but they got an opportunity, and it was a one-off opportunity to get in real close to Europa the other day, which they did. It certainly is going to cost Juno in terms of its orbital plane, but it sounds like it was worth it, Fred.
Very much so. That's right. The flyby was on the 29th of September, and we saw, straight afterwards, some of the, kind of what you might call lightly processed images that come from NASA. But Juno has been especially rewarding for citizen scientists, and some of the images that we've seen of Jupiter's cloud belts have been additionally processed by citizen scientists to bring out some of the nuances of detail, the colours and things of that sort in those cloud belts, and they've been fantastic. And I think NASA, they're all for this because it actually helps the scientists. You find things in there with citizen science processing that you wouldn't necessarily see in the original images. And the great thing is that the same thing has now happened with the Juno images. So we've got this tranche of not over processed, I don't think, but processed images which have been done by citizen scientists who've got a real eye for this work. They kind of mix art and science. There's a very nice demonstration of the effect of it on the Science Daily website. They've got a story titled "Enhance Citizen Scientists Awe-Inspiring New Europa Images from NASA's Juno." And there's a lovely fade from the unprocessed to the processed images of the surface. And it is an extraordinary surface, Europa's ice, the top of the ice layer. In particular, it sort of looks as though it's laced with bits of string, which is or bits of straw. But of course, these are things that are many, many kilometres long.
Well, if you saw that hanging in a gallery, you'd think it was modern art.
You would, that's right. It's exactly what you'd think, which is, fantastic in a way. It is modern art, but it also means something. So these lengths of string are actually probably raised areas on Europa's surface brought about by tectonic action. The fact that this ice layer is not static, it does things, it's in motion, and we know there is an ocean underneath it. It's basically a floating layer of ice on a global ocean on Europa, like it is with several other of the moons of the outer planets. So what we've got is the history of the movement of this ice, which is recorded in these extraordinary string-like features on the surface. And the enhancement allows you to pick up things like, boulders of ice with shadows and things of that sort, which I think really very, very useful.
Extraordinary. And of course, in recent weeks, we've been able to see Europa with binoculars or telescopes.
Indeed, that's right, because Jupiter's still not far from opposition. It's past opposition now. It means it's opposite the sun in the sky. So effectively, it rises in the early evening and is in the sky for most of the night.
Yeah, I've been trying to get a photo of it with my telescope without much luck. I just can't quite nail it. But a few people that do listen to us have published some amazing photos on the Space Nuts podcast group Facebook page.
Excellent.
And, they've done great work.
Yeah.
Great work.
Not surprised to hear that. That's fantastic. Yeah. This nicely dovetails with another story from Europa. And this is kind of more theoretical work, but it's from NASA, and it's from the team that are planning the Europa Clipper, which is essentially the next big thing on its way to Jupiter. I can't remember when it's due to be launched. It's either next year or the year after. I think it's quite soon. So Europa Clipper will be in orbit around Europa, and there we are, 2024. It's the year after next when it'll be launched.
10th of October, to be exact.
Okay, thanks, Andrew. Glad you're there. And it's a bit like Juno. It'll be in orbit around Jupiter, but it will fly by Europa many times. In fact, roughly 50 times will be close to Europa. And it's festooned with instruments. So this is all about trying to work out, what is required from the science that will be done when Europa Clipper is in the vicinity of Europa. And you might remember we've talked about this sort of thing before, because I think it was at the Jet Propulsion Laboratory, and that's where this science comes from. There was this issue of different kinds of ice, whether it's the two names for the sorts of ice that accumulate on the underneath of the ice layer. And there was something, I can't remember, it was something like frizzy ice or something of that sort that was the softer stuff. I can't remember the exact name. But that's the same sort of work that's being done now. And what the scientists are recognizing is that there's actually a good chance that the cryovolcanic activity, to give it a posh name, which is the plumes of ice that might seep out from the surface, the ice surface of Europa, and they might come not from the ocean below the ice, but from more shallow ice lakes within that crust of ice. So the idea is that you have a layer of ice, but because of local, what you might call hotspots, I suppose, with the heat source yet to be determined, you might have liquid reservoirs. And in fact, there is some evidence of this from work that was done using data from the old Galileo spacecraft, which was in orbit around Jupiter for many years, and that there is a belief that there is possibly salty liquid lakes underneath the ice of Europa, which may themselves actually start spurting ice crystals out. It's water as it comes up through the ice, but it immediately freezes when it hits the vacuum of space. So these are the kinds of things that might be looked for by Europa Clipper. What we're seeing here, Andrew, is brilliant preparation for what is going to be a really significant mission when it flies in a couple of years' time.
Yeah, and assuming it gets off the ground as scheduled, it's going to take 6 years.
Yes.
6 years.
It's not a quick place to get to, isn't Jupiter? Takes a while. But that's fine. Hopefully Space Nuts will still be going in 2030 when it arrives there, and we'll might be a little bit older by then, both of us, but I'm
actually planning on stopping the aging process soon, so that I don't, get any older and can still manage by then. But what I'm interested in with Europa Clipper is part of its reason for going there is the astrobiology factor, which Europa promises in terms of potential life-bearing molecules or whatever you want to call them, and maybe even life itself.
Exactly. I mean, we know that Europa in the past has emitted plumes of ice, much like Enceladus does, Saturn's moon Enceladus. And of course, we hit the jackpot with Enceladus with the Cassini mission, which was able to fly through the ice plumes of Enceladus and actually measure exactly what was in there, which also excited the astrobiologists, because there are several things that are interesting for life processes, life formation. And, hopefully the same will be true with Europa. The great thing is, I think Cassini was launched around about 1997, if I remember rightly. We've had getting on for 30 years of progress in terms of the instruments that you might want to fly on a spacecraft. And actually, none of the instruments on Cassini were designed to have an inspection of the ice, flying through the ice plumes of a geyser from the surface of Enceladus. That was all a complete surprise that was happening when the spacecraft got there, and so they had to use what instruments they had, which were never designed with this sort of thing in mind, to do the molecular sampling and all the rest of it, and that was very successful. But now think about going to a moon that might be doing the same sort of thing with the preparation. Is that that you've got a good chance that you might well fly through these these interesting plumes of stuff.
Just by the by, how different or the same are Europa and Enceladus? Have we got any idea?
Well, they're certainly different in that when you look at the images of Enceladus and compare them with Europa, Europa's got all these features on that we've been talking about, the string-like stuff. Yeah. Enceladus certainly has chasms in its ice, but the ice is much, much smoother on Enceladus. And that suggests there is a lower level of what you might call tectonic activity in the ice itself. So that maybe Europa is a more active world in that sense, just because of the fact that there are more of these features on it that reveal the possibility of ice movement. So I think the basic structure, however, is the same, but clearly the details are different, and that might be due to the fact that, well, Jupiter is a much bigger world than Saturn. It's Europa is nearer to Jupiter than Enceladus is to Saturn. Europa is nearer the Sun than Enceladus is. So all of these things may play into making it a more active world.
Yeah, I imagine so. And I think you hinted at it there, but the tectonic activity you referred to would be caused by those gas giants and the gravitational effect.
At least partly, yes, that's right. Yeah.
So with both of these moons, ice moons, ice encasing a global liquid ocean.
Yep.
Does that mean that the ice is sliding around on a viscous surface, or is there some stability?
It does.
I suppose the stability would be there.
You're absolutely... Sorry, go on.
I was right the first time.
You're absolutely right. That is measurable with Titan. So Titan, Saturn's biggest moon, has this same structure, and you can prove by looking at basically the rotation of Titan, the details of its rotation, you can prove that the ice surface is decoupled from the rocky core, that the ice actually slides around on it, because they've got they behave differently as Titan goes around in its orbit. It's really interesting research. That was one of the early pieces of research done as a result of the Cassini mission. And it's what proves that you've got this liquid, a lubricating layer between the rock and the ice, so the ice can just wobble about on it. And indeed it does.
Titan spits out more than just water though, doesn't it?
Yes, well, it does. It also has cryovolcanoes, which are probably water, ammonia and water slush, something like that, coming up from the magma ocean below.
Yeah, nice place.
An amazing world. World.
They are incredible, aren't they? I just find it really fascinating, and maybe it's not a surprise that you've got two gas giants and they both have an ice moon each that are so very close in description and habit, I suppose, Europa and Enceladus. So I think it's amazing.
Yeah, there are others too. think it's some of Uranus's moons are known to have the same sort of phenomenon. It might even be
Is that right?
Might even be Triton, which is one of Neptune's moons. Can't remember the details of that, but they're common. That this structure is common throughout the outer solar system, and indeed Pluto is thought to have this structure as well. Ice over an ocean over a rocky core.
So it might be something that's actually more normal than we would have considered.
Yes, that's right. This fancy stuff with water on the surface is totally abnormal, the kind of thing that we've got here.
Yes, and aren't we lucky?
We are lucky, yes, that's right. Otherwise we might all have fins and be swimming around under an ocean, under an ice.
Well, that could be a thing too. Yeah. Who knows? Yes, we watch with interest, and if you want to check out those images that Fred was talking about, most certainly go and visit the scitechdaily.com website and see what they did to enhance the images of Europa. It's really stunning work. And yeah, we wait with bated breath, although if you hold your breath this long, you probably just die, because the Europa Clipper mission is 8 years away from even getting there. 2 years away from launch, 8 years from arrival, if you start today-ish. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's take a break from the show to talk about our sponsor, NordVPN. Now, I've told you about a virtual private network many times and how important it is to have something like that set up on your, whatever device connects to the internet for your own protection, to protect your personal information, to protect your bank accounts, and to protect your data. Well, Nord is the best in the business. They have very fast, secure networks and servers. They offer not just a virtual private network, they offer different packages which you can pay for monthly, yearly, or up to 2-year plans. And at the moment, as a Space Nuts listener, you get the benefit of 4 months free. So let's, for example, offer you up the complete package, which gives you high-speed VPN, malware protection, tracker and ad blocker protection, the cross-platform password manager. They are fantastic. Everyone should have one of those with all the passwords we need these days. The data breach scanner and a terabyte of encrypted cloud storage. That's all available to you right now for 2 years plus 4 months at a super low price as a Space Nuts listener. Now, if you want to look into this and see what works for you, go to nordvpn.com/spacenuts, and then you just click on the Get the Deal button. And don't forget, there's a 30-day money-back guarantee. That's nordvpn.com/spacenuts. Click on Get the Deal and see which plan suits you with our sponsor, NordVPN. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, to one of the more common topics of modern astronomy and space science, and that is dark matter. And we keep sort of looking for answers to this. We keep getting people popping up with questions about it as to what they think it might be. And we've got one of those a little later today for those who get the question segment through whatever platform they listen on. But this has got to do with gravitational lensing, but they may have come up with some new theories. Is that what we're talking about?
Well, yes. In a way, what we're seeing is a new tool to explore the details of dark matter, because one of the ways that we can explore dark matter is with gravitational lensing. And so we've talked about this many times before. The situation is you've got a very distant galaxy or cluster of galaxies, but in front of it, there is another cluster of galaxies whose gravity distorts space in such a way that it forms a gravitational lens around it, behaving like a glass lens, and that magnifies the more distant cluster and lets us see it. So, and the great thing about that is that it's not just the visible matter in the lensing cluster, the foreground cluster, it's dark matter that contributes to the lens. So you could imagine a situation where you had a cluster of dark galaxies, none of which had, illuminating objects in them, namely stars, but were made entirely of dark matter. They would still act as a gravitational lens because the dark matter itself outweighs normal matter by about 5 to 1. So it's a great tool. Finding gravitational lenses is a great tool for exploring dark matter. they're relatively common, but we only know of, it's something like 100 of them. Many of them discovered by the Hubble telescope. And of course, we're now seeing beautiful images of some of the well-known gravitational lenses from the Webb telescope. But what has happened here, this is some really neat work, which started off in Australia. It's now got other collaborators throughout the world. But it comes about because of a neural network developed by a data scientist at Swinburne University, Colin Jacobs. So what Colin did was looked at thousands of images of galaxies with this machine learning algorithm to find out which of them had gravitational lenses and were showing us distant objects. And I guess, what you're doing, teaching a machine to learn the signs of a gravitational lens. And that usually involves fuzzy, distorted images of the background objects, as well as usually images of the foreground objects as well. But you can teach it to sort of pick out the really likely candidates. And that's what happened. They actually detected up to 5,000 possible gravitational lenses from that machine learning algorithm. But in order to prove that they are gravitational lenses, what do you need? Well, you need spectra. You need to analyze the light from both the foreground and the background objects to demonstrate that they're not just chance alignments, that these are actually gravitationally lensed. Because the spectrum tells you the distance. It gives you the redshift. It's the way that barcode of information comes out of the rainbow spectrum of any object. That tells you how far away these objects are. That's the crucial thing. And so we're now seeing a paper led by Kim Vai Tran, who's at the University of New South Wales here in Australia, part of the Astro 3D consortium. Kim and her colleagues have basically analysed 77 of those suggested lenses from the machine learning algorithm, and 68 of them are actually gravitational lenses. So it's a really high success rate for the machine learning algorithm. And the great thing about this, Andrew, is that they, what they've done, the lenses that Kim Vai and her colleagues have looked at actually span great distances in the universe. So you're looking at a whole range of different look back times, from just a few hundred million years to billions of years, almost, on the horizons beyond which we can't see, not quite that far, because these have been done with ground-based telescopes. I think they use the Keck telescope in Hawaii and the Very Large Telescope in Chile to do their work. Brilliant stuff. And these, of course, are the best facilities in the world for optical astronomy, or among the best. And so, having these extra newly discovered 68 gravitational lenses, a range of distances from us, basically give you insights into how the universe has evolved, because the furthest ones are the ones you're seeing at the earliest cosmic time, and the nearest ones you're seeing at more recent cosmic times. And if you can look at the way perhaps the dark matter clumps on those, across those timescales, or just the way it's distributed in the foreground lensing clusters, it's going to tell you something about dark matter. And heaven knows, the more we can learn about dark matter, the better it is, because one day we might find out what it actually is. So it's a really neat piece of work. As I said, it has international collaborations, I think, including the UK, the US, possibly Korea. I can't remember the exact details of the authorship, but it's a big collaboration and is really excellent work that we hope will actually give us much more insights into dark matter. Sorry, it's not Korea that's collaborating. The other collaborating nation is Chile, where, of course, the Very Large Telescope is situated.
So the crux of the story is they've found a new way of finding gravitational lenses. They've confirmed a whole batch of new ones, and that might lead to opportunities to learn more about what's going on out there, including dark matter.
a perfectly succinct and accurate summary of the story. I don't know why I'm here, Andrew, actually. You can do it all by
It's
yourself.
10 minutes then. Just looking at the website, and they've got images of some of these gravitational lenses.
Yep.
You can actually see the effect and how it all works. It's it is like putting a magnifying glass up, and just you can just see the 3D effect. It's fuzzy, but they can enhance that with computer technology, I'm sure, and when they study these kinds of images. But being able to gather that light from all different parts of the universe through one sphere, if you like, is pretty impressive. It's clever science.
Very clever science, and so well thought through and well executed. Yeah, it's a very nice piece of work.
Indeed it is. All right. Again, if you want to chase that one up, scitechdaily.com is the website. If you want to look at those images, they are really quite amazing when you look at the way they've the way the gravitational lens enhances what you're looking at through various telescopes. Yeah, terrific stuff. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
You're listening to Space Nuts, the podcast about astronomy and space science with Andrew Dunkley and Professor Fred Watson.
Now, Fred, to our second favourite part of the show. Our favourite part is the end. No, this is our favourite part. This is where we turn it all over to the audience to come up with some questions that we may well pass on to someone else to answer. But no, we'll have a crack at them. Or Fred will. I'll just sit here and laugh. Let's firstly head off to a place called Cambridge.
Hi, Andrew and Fred. It's Ian from Cambridge, feeling a little bit sorry for myself as I'm in bed with COVID. I have a couple of questions. As Venus and Mercury are nearer the Sun than Earth, how come we can see the planets in the night sky? And also, another question, looking at photographs of the Earth from the Moon, the Earth always appears very small considering how much bigger it is than the Moon. I wonder if you could explain how that happens. Many thanks.
Thanks, Ian. Get well soon, because, yes, I know what it's like to be bedded down with COVID. They released the results of a study the other day, Fred, that suggested that up to 1/3 of people who've had COVID have had symptoms that lasted more than a week. And I know when I had it, I coughed for about 2 months. So I was one of the statistics they were talking about. So, it can knock you around. But what surprises me is how different the symptoms are from individual to individual.
Yeah.
You know, it affects everybody in different ways. I mean, I had the cough. My wife didn't. Just weird.
When Marnie and I had it, Marnie was sicker than I was. I was sick for basically a couple of days, day and a half maybe. We were, as you remember, we were forced into hotel quarantine in Launceston in Tasmania.
Right.
And we were fine. We just treated it like, got up every morning and we felt okay. I think Marnie's symptoms lasted longer than mine, but not like yours. They weren't still going 2 months down the track. So you're quite right. Everybody's different. And I hope Ian's symptoms in Cambridge subside before too long as well.
Yeah. Well, even when the cough went away, I still felt the urge to cough quite regularly. And if I did anything like go for a long walk or play a round of golf, I'd sometimes find that inhaling, I'd be like I was inhaling steam. I had that sensation. It was very strange. But, it's all gone now, but it took months. So hopefully you won't have to suffer through that, Ian. Now, let's get to Ian's questions. Venus and Mars, yes.
Venus and Mercury.
Mercury, I should say.
Yeah.
They're closer than Earth is to the Sun, so why can we see them? I suspect I know the answer to this.
If they always stayed between the Earth and the Sun, you wouldn't see them. But, of course, they've got each of those is in their own orbit. Mercury closer to the Sun, Venus not quite as far, as close to the Sun. And so what that means is that as they go around in their orbits, their appearance in the sky, basically they wander backwards and forwards, not ever straying too far from the Sun in the sky. But once the Sun sets, or before the Sun rises, they're both visible, usually, and more usually visible than not. And they're only completely invisible when they're either between us and the Sun or directly in line with the sun on the other side of the sun. And the details are, as for example, let's take Mercury. As Mercury moves around the sun, it moves progressively further away from the sun in the sky, as seen from our viewpoint. And at its furthest, what we call the maximum elongation. And that's when it's easiest to see, because it's above the horizon for longer, for example, after sunset. If you've got Mercury at maximum elongation after sunset, then we'll see it in a darker sky because it'll be there for longer as the sun goes down. The actual angle varies by 10 degrees, in fact, for Mercury. So it's between 18 and 28 degrees, the maximum elongation. And the reason why that changes is that Mercury's orbit is actually quite stretched. It's quite elliptical. It's not a perfect circle. Venus, on the other hand, has a much more circular orbit, and so its maximum elongation has less variation, and it's between 45 and 47 degrees. So you can see from that immediately that as far as an angle on the sky is concerned, I mean, 45 degrees is half of a right angle. As far as an angle on the sky is concerned, Venus actually strays quite a long way from the sun. And that's why we see it brilliantly in the evening or morning sky when it's at its maximum elongation. And it's the morning or evening star. It's so bright because of those cloud layers that it's surrounded by. And one other thing is that there are times in its orbit when it's so bright that you can actually see it when the sun's still above the horizon, Venus visible in daytime. I find that less easy to find now. I used to have no trouble finding it, but as my sight has aged, I find it less easy. Marnie is a lot better at it, pointing it out than I am, and she usually points to it and I can find it afterwards. But once upon a time, I had no trouble seeing it. And the other thing, just for Ian to think about, is the shape of these worlds. For example, Venus, when it's at its furthest from the elongation from the sun, it's got a sort of half moon shape because half of it is being illuminated by the sun and the other half isn't. When it's coming to that position from behind the sun, it is gibbous. It's a bit like a gibbous moon, fatter than a half moon. But as it slides between the Earth and the sun, it becomes an ever decreasing crescent in shape, but getting bigger because it's getting nearer. So the crescent shape of Venus is well worth having a look at it in a small telescope when it's coming between us and the sun in the evening sky.
Sounds good. We've got a couple of gibbous out at Western Play Zoo.
Well,
you can actually hear them from this far away where we live. We're in West.
You can, yeah.
And they really raucous of a morning because the male's very territorial, and he'll do something akin to a John Travolta dance.
Okay.
And make a hell of a racket and puff his big neck up and whoop, 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 and he's basically threatening people because this is my territory and stay away.
Yeah, stay away.
And they're designed to boom out this sound that carries for kilometres and kilometres. So I quite often hear them in my backyard. It's really strange living here and hearing lions roar. And
yes, I know. I've heard the lions roar there as well.
Yes, and the waning gibbous of a gibbon. They're amazing creatures, though.
Yep.
And all right.
So the rest of Ian's question.
Yeah, well, there was a second half to the question. So the size of Earth as seen from the moon, why does it seem so small? I've seen photos that vary. I mean, I've seen one famous photo where there's this just big ballooning Earth over the moon's horizon, and then other ones where, like it's just little ball in the sky. So, yeah, that's a good question.
And it all depends on the focal length of the lens that you take the picture with, because that's all about magnification, So if you use it with a wide-angle lens, the Earth will look small. Use a telephoto, it'll look big. But in reality, I guess the one of the things is that because the lunar landscape is so alien, you don't have anything familiar to compare it with. If you were, looking at an image of the Earth taken from the moon when the Earth was low down on the horizon, there's no trees or church spires or skyscrapers or whatever to compare it with. The bottom line is that if you were standing on the moon, yes, the Earth would look 4 times bigger than the moon looks from the Earth because that's its size, and of course the distance is the same. So it would be quite significantly large, and a full Earth, which is what you'd see from the moon when it is new, as seen from the Earth, because you're on the dark side of the moon, you'd see a full Earth in the sky. It would be almost as bright as daylight, that full Earth illuminating the surface. And that's why we can see the old moon in the arms of the new, that Earth shine thing when we look at a crescent moon.
Gosh, it'd be just so amazing to be able to stand up there.
Wouldn't it? Yeah.
Back at Earth. I can't imagine it. I'm pretty sure photos wouldn't do it justice.
Wouldn't do it justice, that's right.
Yeah. But, Ian, it's a trick of photography, basically, that causes the effect we're talking about. Thanks for your questions. Get well soon. Now we'll move to Washington.
Hi, guys. This is Gus Iverson from Issaquah, Washington, in the United States. I asked you a question a couple of weeks ago about an ant wandering around a string representing multiple dimensions in a single-dimensional space. I have a new question regarding quantum-type problems, and that is, if we're looking for dark matter, what about the fact that while our bodies are composed of atoms and they're so far apart, and we still, run into things like walls and each other, what if the dark matter and dark energy is the things that provides us with corporeal substance at this macro level instead of the atomic space? Thanks, guys.
Wow. That's a great question.
It is, yeah.
Deep there, Gus. Hang on, I'm just going to get my gravitational lens out and see if we can. There we go. How's that?
Yeah, that's right. Yeah, it's a good one.
If you're watching on YouTube,
I can still see your lens. I can see your gravitational coffee in the bottom of it.
Yes, it's right. I didn't quite get it all, did I?
But it's the wrong shape for a gravitational lens, Andrew. If you want to simulate a gravitational lens with glass, it's the bottom of a wine glass, the stand of a wine glass with that cusp on it.
Yeah, we've talked about that before.
That exactly simulates a gravitational lens. Far better than your empty coffee cup.
The wrong time of day for one of those glasses.
Yeah, it is, yes, that's right. So back to Gus. I quite like this idea because probably not for dark energy. Dark energy seems to be a property of space itself. But dark matter, we think, is more like normal matter, but of course, it doesn't interact with it in any way that we can discover. But if you had a dark matter particle that was sort of an equivalent of the Higgs boson in the real matter world, the normal matter world, could it contribute to that, that phenomenon of making bundles of atoms feel like something really solid? And the answer is, I don't know, but it's an interesting idea. It's an interesting idea, and and I think that's one of the intriguing things about dark matter. We have this. When we think of normal matter, we've got this suite of 17 fundamental particles, 16 plus the Higgs boson, and they're electrons and top quarks and bottom quarks and things of that sort. All of that stuff that is recognized as being the standard model of fundamental particles. And then we've got dark matter, which we only know about because galaxies don't fly apart. That's one of the symptoms, and because we can see its evidence in gravitational lenses. So it is definitely there, but we tend to think of it as just one type of particle, whereas there might be a whole standard model for dark matter as well. So you might have, dark matter electrons, dark matter top quarks, dark matter charm quarks, all of these funny things that they have in normal matter, they might be in some way replicated in dark matter. And I think that was the principle of supersymmetry, the idea that SUSY, as it's called, supersymmetry, that might provide the theoretical framework for such a body of dark matter particles. But supersymmetry seems to have fallen flat on its face. There's been absolutely no evidence of supersymmetry being found at facilities like the Large Hadron Collider. So we're not really much further along with that. But I like your thinking, Gus. That's probably as much confirmation as I can give from my point of ignorance in fundamental physics. But
Fair enough.
Great stuff.
I suppose we should also point out that the naming of dark energy and dark matter is creating a problem because people connect the two, and the naming is bad.
Yeah, it is. It is. They're quite different entities and different problems. And I think we'll know what dark matter is before we find out what dark energy is.
Indeed. Thanks, Gus. Great to hear from you. Now, remember the other day, Fred, I was doing a terrible impersonation of what an astronomer sounds like when they get excited.
I've wiped it from my memory.
It's prompted a thought from Buddy.
Hi, guys. It's Buddy from Oregon again. I was listening to that 46, and you guys were kind of making fun of particle physicists and how they sound when they get excited. And then you were talking about astronomers. I think astronomers are probably the most easily excitable people in the world, to be honest. Who else gets that excited over something that happened a billion years ago? Thanks, guys.
That's a great comment.
It is. It is. And we've been doing it. We've been doing it today. We've been excited about, things that happened a billion years ago. Yeah, he's got a point, has Buddy, actually. But it kind of resonates with something I've always said, that astronomy is not a discipline, it's an illness. People get sick with astronomy.
Yes, indeed. Buddy, thank you for your comments. I appreciate it. We don't always have to run with questions. Sometimes people come up with just lines for us to deliver, and happy to share that with the audience.
Very much so.
Now, if you have questions for us, don't forget to send them through on our website, spacenutspodcast.com or spacenut's.io. We own both URLs. We are URL
rich.
I can't give a description. Addicts. So, yes, you can go to either of those. I'll send you to the same place, which is a different URL. Don't ask me. You can put your questions in there through the AMA tab. You can send us text or audio questions, or you can click on the tab on the right-hand side, which is send us your audio question. And, we'd love to hear from you. You can also have a bit of a browse while you're there. The Space Nuts shop, the Astronomy Daily tab, where news update very, very regularly. I did notice with Astronomy Daily, now that I do the Astronomy Daily podcast, and that's where I get most of my information, that occasionally we'll just randomly pick a story from 2016 or something like that. So just ignore that. But occasionally, it's nice to read old stories occasionally just to see what we were thinking about a few years ago and whether or not it's changed. But, have a look around. Don't forget the Space Nuts shop as well, where there's lots and lots of goodies that you can get your little mitts on. And, that's it, spacenutspodcast.com or spacenuts.io. It's all over, Red Rover. Fred, thank you so much.
It's a pleasure, Andrew. It's been a great show. It's nice to talk about why astronomers get excited, as well as getting excited about the astronomy. Yeah, it's good stuff.
Indeed.
Thank you, Andrew. We'll speak again soon.
We will. Thank you, Fred. Professor Fred Watson, astronomer at large. And from me, Andrew Dunkley, thanks for listening. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.